talk about uncertainty for a little bit. By now you're familiar with the idea that we're doing addition, subtraction, multiplication, and division for different calculations in this class. But now we're going to go a little bit deeper than just going based on the rules of significant figures. So I kind of want to show you how this idea of uncertainty reflects onto the idea of significant figures. And this actually has a statistical background that makes the entire business a little bit more robust than we make it look at first. In particular, when you're adding or subtracting, right? So you're adding x and y or subtracting them from each other to get a new value. You would normally add or subtract the values. But if each one of those values has an error associated with it, then the error could be anything. It could be an error associated with the instrument that you're using to make the measurement in the first place, or it could be the error bar of your ruler when you're measuring the length of something, or even a systematic constant error that that's there every single time that you make a measurement. You basically have this delta x in association with x, and that's the error of x, and then delta y is the error of y. And so what happens is that when you're adding numbers that have errors associated with them with each other, or when you subtract them, you need to account for the change that's going to happen to the error. And it's not exactly a summation subtraction approach that needs to happen. In particular, statistically speaking, what has to happen is that you have to square the errors, the individual errors, then add them together, and then take the square root of that. And that's actually how you find the error when undergoing addition and subtraction. But when you do multiplication and division, right, so you are either multiplying x and y together or dividing them from each other. If you have errors associated with those measurements, there is a statistical method to determine what the new resulting error is going to be. And it's a little bit more complicated for multiplication and division. In particular, we have the errors divided by the original value all square, adding all of those ratios together, and then taking the square root of, and finally multiplying that resulting value by the answer of such multiplication of division for the regular numbers. So I'm going to show you how this kind of works out, and ultimately how it just kind of takes you back to the shortcut way of doing significant figures, which is that for addition and subtraction you just keep an eye out on the lowest number of decimal places, and for multiplication division, you just keep an eye out for the lowest number of sig figs. You'll see how this is going to play out, and I'm going to show you an example for multiplication and division first. So here we go. Let's say that we are, actually we're going to do one for addition. So if we add these two numbers together, so we have 2.347 plus 4.18. We get 6.527 out of that. But then we have errors associated with those two numbers. Since this is an addition, we have to carry out the squares of the individual errors, take the square root of that, and find out what the value is. So squaring the values inside and adding them together yields 1.04 times 10 to the negative 4. Taking the square root of that value gives us a value of 0.0102, which is the error of the final answer. Now this is the interesting thing. The error is always going to dictate the level of certainty of your number, and because of that you're always going to go with the highest value of your error. So we got the 0.0102 value right here. You want to go with the highest value, which is the 0.01, right? That's the first significant number that appears in this error, but that number appears on the second decimal interval. And what that means is that when you couple it now to the final answer of the addition, well, you basically are restricted to the highest value of the error, which is the second decimal place, which automatically restricts the answer to the second decimal place as well. So you wouldn't write the answer here as 6.527, you would just write it up as 6.53, because that will keep it up until the decimal place for which you have the highest error bar present in your delta Q. Now the shortcut, of course, is just to look at the decimal places, 2.347 and 4.18. The first number has 3 sig figs, the second number has, 3 decimal places, and the second number has 2 decimal places. So the answer has to have the least number, which is 2 decimal places. So you end up with the final result, which is the same thing as before, 6.53. But what you can see here is that now you have not only acquired that value, but you have now a very good estimate of what the error of your calculation is. And so this helps you keep an eye out on the error as you're carrying out calculations, and you propagate the error properly so that you have a clear idea of what level of certainty and precision you're actually dealing with. All right, now in the laboratory, what you would normally be doing is making measurements, either of mass or volume. But I want to talk about the measurements of volume for a second. In particular, we have graduated cylinders, which are made to take up a certain volume. It could be a larger volume, like we have a 100 ml graduated cylinder here on the left side, and over here we have a smaller volume, 10 mLs. Now, if you look at the reading, the idea is that you have to pay attention to the innermost ticks, in particular the space in between them. So notice that in the big graduated cylinder, the big marks are in volumes of tens, right? So it goes from 50 to 60 mLs to 70, etc., etc. But then you have these marks in between, and if you count them, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you have marks that go down to single units, right? So this will be 51, that will be 52, 53, etc., etc. But the difference between the marks is 1, right? So 55 minus 54, 1. So the level of precision that you have in these graduated cylinders is pretty much all the way down to the single unit. So when you look at a mark, like if this was the meniscus of the liquid that you're looking at, well, this sits just above the 45 millimeter mark. So you would definitely read that and say, okay, so it's above the 45 mark, so for sure you read it as 45. But because you have the inner ticks, right, and this is not exactly falling right above the mark, but somewhere, past it, you have to guess the next value, the value in between. And as I said before, the graduated cylinder here gives you, in terms of precision, up to the first unit, right? So 45, the 5 is the unit, but now we're going to go a level further than that. And over here, if you look carefully, notice that the mark of the meniscus falls above 7, but you have this inner tick still. And if you count the inner ticks, you'll say, okay, this falls just above the 7.7 mark, below the 7.8. So the mark that you want to go with is 7.7 because you haven't quite reached 7.8. But that's based on the ticks. You still have to guess the next value, which is the in between. So based on where they fall, you would say that this one somewhat reasonably could be 45.4. And now this one is the value that you're guessing. The value that's not given with an actual tick is the in between. And same thing here. You have gotten the 7.7 just from the tick marks, but now we're getting the extra 9 from the in between. It's very close to 7.8, but it's not quite there, so it's probably 7.79, 7.78, and that's the guess that we're making. But we're going that extra step, right? So it's not just reading the lines of the graduated cylinders, it's just going that extra step. So what this basically tells you is that depending on which graduated cylinder you're using, your level of precision is actually different. Notice that for the big graduated cylinder that allows you to measure higher volumes, that's kind of convenient if you have to measure volumes greater than 10 mLs. But it comes with a caveat that your precision is only good up until the first decimal point, because that's the point where you now have to make a guess. Whereas if you use a smaller graduated cylinder, the guess doesn't occur until the second decimal place. So you have a precision of 0.01 mLs plus or minus, roughly speaking. So that's the error that you're dealing with in that respect. So, and notice the other thing, both of these numbers are 3 significant figures of worthness or significance, but their precision is different just because of the tick marks that you have. So you have to keep an eye out for which graduate cylinder you're dealing with. What's the volume difference between the ticks. Another thing to point out is that volumetric flasks, like the one shown here on the left, or volumetric pipettes, like the one shown here on the right, they are very precise volumetric equipment that we have in the laboratory, a lot more than graduate cylinders. So this particular values, whatever the number is, so here is 250 mLs, which is the volume of this flask, so long as you bring the liquid meniscus line right above this line right here that you see, going horizontally, that white line. Same thing here for the pipette. There's a line that if you just have the meniscus right above it, it's guaranteed to have the volume depicted right here. But because these are made much more accurately than graduate cylinders, you actually have two levels of decimal places worth of significance. So what that basically means is that the 250 ml graduate volumetric flask, excuse me, is going to have a total of 5 sig figs, right? Because the last twos here are actually worth significance and precision. If you look at the glass, you can actually see here that, yeah, this is plus or minus 0.24. Here in the glass, it will say plus or minus 0.02. So that you can read directly from the actual glassware. But, the key point that I'm trying to make here is that you can't just assume that because you have a flask that looks a certain way, that you already have 4 sig figs or 5 sig figs or 3 sig figs. That's not necessarily a constant. What is constant, however, is the precision based on either the type of glassware you're having. So in this case, volumetric flasks or pipettes can have up to 2 decimal places worth of precision. And depending on the actual volume, that could be 5, 4, or even 3 significant figures. So just be careful about that. And specifically when dealing with titrations, which we'll talk about in the future, you want to make sure that you give those volumes, the readout to those volumes to 2 decimal places. Okay, now a final thing just to mention here is that there's other glassware that we also use to measure volume, but they are a lot more inaccurate. One of them is the Erlenmeyer Flask, shown here on the left side, and the other one is the beaker, shown here on the right side. And if you try to make a measurement with these things to any level of precision, you'll realize that your precision is very lousy. This is a 125 ml flask, and the marks that are actually present on the flask have a difference of 25 ml volume. So pretty much, if your line falls somewhere in between them, you have a plus or minus. If you're good, if you can actually kind of do this, but looking at this thing, kind of like visually separate it into equal marks, maybe 5 marks, then the best you could do is maybe do a plus or minus 5 mLs of precision. Here it's even worse because you're dealing with a 600 ml beaker. So if you go in between the marks, this is 100, 150, 200, right? There is a 50 ml gap in between, which if you do like something similar to what we did right here, then maybe this is a plus or minus 10 ml gap. And it's, needless to say, that's not very accurate, right? If you have a 10 ml uncertainty in your actual volume, this is not going to be good. So long story short, beakers and Erlenmeyer flasks are going to be good for carrying out reactions, for transferring liquids, but they're not good for actually measuring the volume of liquids, especially if you're counting on precision in your measurements. All right, so no decimal place for either of these two measurements. All right, so that's it for this one. In the next video, we'll talk about rounding and performing calculations.